Hello students, welcome to my channel Physics by MKR. In my previous video, we discussed about the classification of physical quantities. Today, we are going to discuss about the classification of system of units. First of all, what do you mean by unit? Unit is a standard used for the measurement of any physical quantity. Then, how many units are used for the measurement of any physical quantity? There are number of units you can use situationally, and all of them are called practical units of that physical quantity. Practical means suitable for that measurement. For example, if you want to measure the thickness of a wire, we use millimeter as unit of measurement. And a little big, centimeter is used. For the dimension of a room, meter is used. For distance between two cities, kilometer is used. And for interplanetary distances, a big unit light year is used, which is nearly 9.46 into 10 to the power of 15 meter. And even a big unit of length is there, which is called light year of length, called parsecond, which is 3.26 light years. Similarly, for the measurement of mass, we use milligram as a small unit, and gram, the next big unit, kilogram, the next big unit, and quintal, which is 100 kg, and metric ton, which is 1000 kg. These are all the units we can use for the measurement of mass. Even there is the biggest unit of mass called Chandrasekhar limit, which is used for the measurement of the masses of planets. It is nearly 2.8 into 10 to the power of 30 kg, which is nearly 1.4 times to the mass of Sun. And regarding time, the units used are second, minute, hour, day, week, month, year, so on and so forth. But all these units are called practical units. But as we said earlier, science is the systematic study of nature. Similarly, we must have system of units for the measurement of physical quantities grouped together. So far we have 4 systems. In the previous days, we used FES system, which is also called British system. And later, the metric system or French system, which consists of 2 systems, namely CGS and MKS. Later, this MKS system is upgraded into SI system, which includes 7 fundamental quantities. And the units in those systems are, in FES system, the length is measured in foot, mass is measured in pound, time is measured in second. In CGS system, length is measured in centimeter, mass in gram, and time in second. In MKS system, length is measured in meter, mass in kilogram, time in second. But the standard SI system includes this MKS system. That's why the 3 quantities units are same as in MKS system: meter, kilogram, second. But in SI system there are 7 fundamental quantities. That is why the remaining 4 quantities are measured like this: current in ampere, temperature in Kelvin, luminous intensity in candela, and quantity of matter in mole. Some prefixes are used in representing practical units, and simply numbers expressed in powers of 10. For example, milli is 10 to the power of minus 3, centi is 10 to the power of minus 2, deci 10 to the power of minus 1, micro 10 to the power of minus 6, nano 10 to the power of minus 9, and pico 10 to the power of minus 12. Similarly, kilo 10 cube, hecto 10 square, deca 10 to the power of 1, mega 10 power 6, giga 10 power 9, tera 10 power 12. And every physical quantity possesses only one systematic unit, and all the other units are come under practical units. For example, the SI unit of length is meter only, but millimeter, centimeter, kilometer, and any other unit come under practical units. So, similarly, mass has SI unit kilogram, and all other units come under practical units. That means a physical quantity possesses only one systematic unit, and all the remaining units come under the name practical units. But all practical units are related to SI system unit with the help of these prefixes. For example, 1 kilometer is equal to 10 cube meter. Kilo means 10 cube. That's why 1 kilometer is 10 cube meter, that is 1000 meter. Just like that, these prefixes are used in representing or relating practical units with the SI units. And the speciality of SI units is they are very standard, they are reproducible, and they are measurable, and they are same for all countries, are internationally accepted. That's why nowadays we are using only SI system as a systematic system. Regarding the units of derived quantities, just like fundamental, the units used for fundamental quantities are called fundamental units. The units used for derived quantities are called derived units. And the units used for supplementary quantities are called supplementary units. Just like derived quantities are derived from fundamentals, the derived units are also derived from fundamental units by the method of multiplication or division or by both. For example, first of all, before going to the derived unit, we must know the structure of the derived quantity. The structure means how it is prepared with the involvement of fundamental quantities. That means how many fundamental quantities are involved in the derivation of the physical quantity and how many times each fundamental quantity is involved. For example, if we take any derived quantity, say U, it may contain mass, length, and time. And mass A times, length B times, and time C times, which means the dimension of U in mass is A. The dimension of U in length is B. The dimension of U in time is C. For example, if you take the area of a rectangle, it is the product of length and breadth. But breadth is also length. That's why area is equal to length into length, equal to L into L is equal to L square. But there is no mass here, that's why we are putting 0. There is no time, we are putting 0. Ultimately, in a systematic manner, it is m0, L square, T0, where A is 0 here, B is 2, and C is 0. In this way, all derived quantities, first of all, we must know the structure of the derived quantity in the form of dimensional formula. And next, by substituting suitable units for mass, length, and time, we can get the units of derived quantity. For example, in SI system, what is the SI unit of area? As you know, length is measured in meter. The SI unit of area is meter square, because length is meter and length is meter. Meter into meter is meter square or square meter. In this way, we can derive the units of any derived quantity, provided you know the dimensional formula of that derived quantity in terms of the fundamentals. And basically, what do you mean by dimension? Dimension is the power to which the units of the fundamental quantities are raised to represent the unit of derived quantity. Which means how many times mass is involved in this derived quantity, how many times length is involved in this derived quantity, and time is involved in the derived quantity. Regarding the representation of the dimensions, which dimension is more, which dimension is less, and if you are asked to represent the dimensions in the increasing order, for example, if you take velocity, it is the ratio of displacement and time. That means displacement by time. Displacement is nothing but length by time, and there is power 1 here for length and time minus 1. Because there is no mass, we are putting 0 here. Therefore, the dimensional formula of velocity is m power 0, L power 1, t minus 1. That means the dimension of velocity in mass is 0, in length is 1, and in time is minus 1. So, the negative power is treated as less than 0 power here also. That's why if you are asked to arrange the dimensions in the increasing order, this minus 1 comes first, and later 0 and later 1. And what is the total dimension of velocity? If the question is like this, then the sum of all the dimensions, 0 plus 1 minus 1 is nothing but 0. And there are so many such quantities having total dimension 0. This is possible if some dimensions are negative and some dimensions are positive. And in the case of power, it is the ratio of work and time. And ultimately, the dimensional formula of power is m power 1, L square, t minus 3. That is, the dimension of power in mass is 1, in length is 2, and in time is minus 3. Similarly, in the increasing order, it is minus 3, 1, 2. And the quantity that is having negative dimension in power is time. And the total dimension of power is 0. So such questions are possibly asked in the case of dimensional formula. And there are so many quantities having no units and dimensions. For example, if you take relative density, it is the ratio of density of substance and density of water. Both in the numerator and denominator, you are having density. So the two units, density units here, density units get cancelled, and that remains as quantity without units and dimensions. If you take any trigonometrical function like sine theta, cos theta, tan theta, they are also the ratio of lengths which have no dimensions. That means wherever you come across a physical quantity expressed as the ratio of two same quantities, that becomes unitless and dimensionless. But there is an exemption for supplementary quantities. Here, if you take plane angle, it is no doubt the ratio of two similar quantities, but they are specially attributed with units. In the case of circle, that makes an angle 2 pi at the center, we measure it as circumference by radius. The circumference is 2 pi r, radius is r. So the angle made at the center of the circle by the total circle is 2 pi radian. Though circumference is length, radius is length, length by length cannot have units, but these supplementary quantities are specially provided with units. That's why they are kept aside as supplementary. And another physical quantity which is having no units and dimensions but having attributed unit is solid angle. For example, you take the angle made by the side face of the sphere and its center is nothing but surface area by radius square. Area is the length square, radius square is also length square, length square by length square gets cancelled, and actually it should not have units and dimensions, but is specially given a unit steradian. That's why these two physical quantities are exemptions from this quantities having no units and dimensions. That's all. In my previous short video, I put a question for you. Is length a vector or scalar? Length is a general quantity. It may be used for distance and also used for displacement. If it is used in the place of displacement, it is a vector. If it is used in the place of distance, it is a scalar. That's why length may be vector or scalar. But all other six fundamental quantities are definitely scalars. There is only possibility for length to become a vector if it is represented in the place of displacement. My dear students, thank you for watching my video and please put comments on this for any improvement.